Hello everybody, my name is Aman. I am a 2023-2024 BC Calc student from Egan High School from Miss Elliott's class. I'm going to be making a video on integration using partial fraction decomposition, but I'm going to be going a bit more into like some tips and tricks when doing partial fraction decomposition, some of the things to remember while doing it, and overall just ensuring that you watching this video can gain a cohesive understanding of how exactly and when exactly to do integration using partial fraction decomposition. So just to start off with, I'm just going to start off with what does it mean to decompose a fraction? What does the term partial fraction decomposition even really mean? The main idea behind it is you're just simplifying what we call a proper rational function into, I worded it as smaller bites. You're really simplifying it down into smaller fractions. So when you look at this is what's known as a proper rational function. I'll go a bit more into that in a bit. But when you're looking at a really complicated fraction like this, where you have polynomials on both the numerator and denominator, basically what you're doing in partial fraction decomposition is you're simplifying a proper rational function like this into smaller fractions, into smaller bites. You'll see what I mean by that as we go through the problems. But that way, when you have these smaller fractions, you can integrate them more easily. Integrating this problem as it is right now would be very difficult if you weren't able to simplify and break down the problem into sort of in a way, multiple separate problems. So that's just a general definition. Here I'm going to go a bit into some things to remember when doing partial fraction decomposition. Firstly, start off. Partial fraction decomposition is primarily an algebra-focused skill as opposed to being a calculus-focused skill. Obviously, there's the part of doing this where you do have to integrate the problem. There is the integral side of it. But when you're decomposing a proper rational function, you are effectively having used a lot of algebra to simplify that function and break it apart. So the thing to remember is when you're doing this is just to remember to ensure that you are writing smartly and that you are organizing your information and that you're organizing your algebra such that it is understandable. But it's in a lot of ways, it's more of an algebra skill than it is a calculus skill. The general process is, I'll call it tedious. It's long, but it's not really that complicated when you think about it. Again, it's a lot of algebra, but not really a lot of new calculus. I said this earlier, be careful with how you organize your steps and information. If you end up getting an FRQ on the AP test where the AP reader wants to see you do an integration problem using partial fraction decomposition, using partial fractions, you're going to want to ensure that you are organizing your information such that it is understandable to the reader, that it flows, and that your steps are understandable from where you're going from one point to the next. Lastly, you can be asked to solve definite integrals on the AP test. Definite integrals of partial fractions on the AP test. Now, in the case of this video, however, I'll only be covering indefinite integrals. I have only one example. That's all the time that I'll have for tonight. But in the case of definite integrals, you would basically decompose and simplify the integration problem, and then you would solve it and get a final value like you'd normally do so for any other definite integral problem, where you'd plug in the boundaries and so on. You've done this before. But just for now, I'll only be covering indefinite integrals where we get a final function, should I say, after integrating. Next up, when would we use partial fraction decomposition? I mentioned this earlier. You want to use partial fraction decomposition when you're asked to integrate a proper rational function. Now, what does that mean? Well, let's look at this problem here, for example. This right here is an example of a proper rational function. How do I know that? Well, if we look at the denominator here, this denominator's highest power is x squared. That's to the power of 2. And the numerator only goes x to the power of 1. your denominator has essentially a higher power than the numerator. That's what makes this a proper rational function. On the other hand, an improper rational function would be something like this, where your denominator would be x to the 1, and your numerator would be something like x to the power 2 or x to the power 3, where your numerator has the higher power. In this case, you want to do long division in order to simplify this problem. You want to do long division in order to ensure that you get just a single polynomial, and in which then you just integrate that polynomial like you would for like any other polynomial problem. Like you basically do reverse power rule, yada yada, so on. I will not be covering long division. That doesn't really deal with partial fraction decomposition. But yeah, that's just so for you to know. Make sure, first step you always want to do when you're dealing with maybe a really big complicated problem is ensure that you're distinguishing between, do I want to go with partial fraction decomposition because it is a proper rational function, or do I want to go down the long division route because it's an improper rational function? All right, so we're going to start off with just the one example problem here. Oh, that's my bad. Here in this problem, first thing we want to make sure, I just said this, is this a proper rational function? Yes, it is. We can see that because the denominator's highest power is x squared, numerator's highest power is purely x to the power first. This is a proper rational function. Next up, the thing you want to look here is, in this case, you also want to make sure that in general that you have, I want to say you have a complicated problem, but make sure you have something where it's like you have two polynomials, one on the numerator, one on the denominator, and this isn't really a problem that you could do using u substitution or integration by parts. And so in this case, if we look at a problem like this is not really easily solvable via u substitution or using Lipit. So in this case, our next step is looking at the denominator and seeing if we could just simplify that denominator. So in this case, we're going to simplify that denominator down to 1 minus 2x over, if I'm correct, this is x plus 1, x minus 5. That's what that simplifies down to, dx. All right, so now we've simplified that. Now here, we're going to do, I'm just going to write this out first, and then I'm going to explain it in a bit. I feel like that's the best way to do this here. Here, in this case, A and B both refer to constants. And I'll explain what those constants really mean in a second. But here, this is where sort of the decomposing initially occurs. You can see here, I sort of split the problem into two. One side has the x plus 1 as the denominator. The other side has the x minus 5 as the other denominator. A and B, like I said, are both constants in this case. And basically, in this case, this is going to eventually we're going to find what A and B are. And this is going to allow us to basically integrate each of these sides separately and really get to an answer a lot easier, and get to an integral a lot easier as opposed to having to try and integrate this. Yeah. And so basically, yeah, this is just what you want to do here, something like this. Yeah. And so then your next step you want to do is you want to find a way to get rid of these denominators. Zoop, zoop. And the way you do that is basically you just multiply each side by their respective denominator over each other. So like basically like for this side, the left side here, a over x plus 1, you would multiply it by x plus 1 over x plus 1, right? The right side, you do x minus 5 over x minus 5. And what that should get you to is that should get you to something that looks more like a polynomial that isn't like a fraction. So in this case, you'd end up with something that looks like a x plus 1 plus b x minus 5 dx. And actually what we're going to do here is we're going to simplify this even a bit further. just to ax plus 1a plus bx minus 5b. Oh, a's and b's, not the same thing. Look, I only learned my ABCs until I was 4, so yeah, whatever. Okay, we're moving on. Anyways, so then we get to something like this. Now, here is sort of where things can get a bit tricky, but just stay with me here. It's not really a complicated process when you think about it. The next thing to do is you want to go back to your problem, and you notice that I sort of got rid of the numerator somewhere around here, and I didn't really touch it beyond this point. Here, we're going to go back and look at the numerator, and we're basically, in a way, we're going to segregate each of these terms based on their powers. So here, we've got two terms in the numerator. We've got a 2x, and we've got a 1. This 1 here has a term of x to the power of 0. The 2 here has a term of x to the power of 1. And so what we're going to sort of do is we're going to do something funky. We're going to like split up sort of like this equation into like a set of system of equations. So what we're going to do here is you'll notice here we have this sort of pattern. Here we've got, I mentioned back here on this side, we had an x to the power of 1 term, the 2x here, or actually should I say minus 2x it is. In this side here, you'll also notice we have two of these where we have x to the power of 1s. We have ax and bx. Those are both x to the power of 1 terms. And so what we're going to do is we're going to create a system of equations where it's going to basically be negative 2x is equal to ax plus bx. You'll notice like not everything here I'm explaining. Just trust that this process works. And you'll see in a bit like just kind of how neatly everything arranges. But yeah. And like it's okay if like not all of this makes entirely sense to you at this moment. You'll see how everything fits though in the end. So you'll notice we sort of organized like those terms, those like terms together. I think that's the right word for it. And you'll also notice we can cross out these x's now. So this negative 2x equals ax plus bx can actually just be simplified down to negative 2 is equal to a plus b. And then here, we would do the same thing for the other term in this case. 1, which 1 in this case does not have, it has essentially, it has an x to the power of 0 connected to it. Over here on this side, you'll also notice we have two terms that also have an x to the power of 0 connected to it, 1a and negative 5b. So in this case, you could have 1 is equal to a minus 5b. This right here is going to essentially be the basis for how we find what these constants were in the beginning. You notice, like, I told you what these constants were, but I didn't tell you that we were going to eventually find them later. Here is where we're going to find out what those constants are. So here, we've got two systems of equations. The best way to do this is find a way to cancel out one of the terms, a or b. In this case, I see an a on the top and an a on the bottom, both of which are just of multiples of 1. So what I think we can do here is I think we should just multiply the second equation here by negative 1, all the terms. So eventually you should get something like this. And now if you were to solve this set of system equations, you'll see that these terms would cancel out to basically produce nothing for a. Your a is now gone. B plus 5b is 6b. And negative 2 minus 1 is negative 3, which would mean that b is equal to negative 3 divided by 6, which is negative 1/2. Now, we can just plug back b back up here into this equation, and then which would mean that a is equal to negative 1.5, if I'm correct on that. Let me just make sure. Yep, that's correct. All right, so now you've got what a and b are. So now I'm actually just going to move all this information off the side here. And we're just going to draw an arrow like that. And then we're going to draw another arrow like this. So now we should be able to simplify sort of our equation up here and but this time actually have the values of those constants. So going back here, a in this case was negative 1.5. I'm actually just going to do negative 1.5 over x plus 1 plus b was negative 1/2, negative 0.5 x minus 5 dx. All right. So then now what do we do here? Now we can just what we actually can do here is we can split this integral into two separate integrals. So this here should be equal to, I'm running out of space now. I think I'll just move down to the bottom once I run out of space here. We can just split this up into negative 1.5 x plus 1 plus negative 0.5 x minus 5 dx. Hold up. I just copied the same equation over, didn't I? Let's just do a bit of rearranging. There you go. That looks about right. Great. And now we can just solve each of these integrals separately. So recall that we can actually take out each of these numerators outside of the integral, because in a way they're sort of being multiplied inside of the integral. So actually each of these should also be equal to negative 1.5 of the integral of 1 over x plus 1 dx plus negative 0.5 of, give me a second to rearrange a bit, negative 0.5 of the integral of 1 over x minus 5 dx. All right, and now here, at this point, you probably are starting to figure out how to solve this. At this point, it's pretty self-explanatory, assuming you know the Allen rule. In this case, this answer would be negative 1.5 ln of the absolute value of x plus 1 minus, oh boy, I really am running out for remaining die, minus 0.5 of ln of the absolute value of x minus 5. And the last thing you want to remember is do not forget the plus c. Do not forget the constant in indefinite integrals. So here I'm adding on that, and I mean, as far as I see, that seems like it's the full answer. Yeah, so we're just going to go ahead and circle that. So now this equation right here is equal to the integral of 1 minus 2x over x squared minus 4x minus 5. So that's it. I hope that made sense to you. Final notes, there are several ways of organizing your information when conducting integration using partial fraction decomposition. Be open to looking up how other people organize their steps. My way is just one way of doing it. I know in the case of A and B here, like figuring out what A and B are, another way you could also do it. This is actually the way I ended up doing it on the AP test, but then I found out this way, and I figured this way was easier to understand for you guys. What I end up doing is how do I word this? I move A to one side of the equation, move the constant to the other side where it's by B for one of these equations, and I basically take that equation and put it inside of A. So like, for example here, like another way I could do this is I could add 2 to one side and A to the other. So in this case, I would get something like A is equal to negative 2 minus B, if I'm correct. Yeah, that seems about right. And then basically I would take this A and I would plug this equation into here, if that makes sense. And that way, then you would only have B's in that equation. And that way I would be able to figure out what B is. And then I would substitute B up top. And then I would be able to figure out what A is. Does that make sense? I hope that did. Yeah. And last but not least, integration of fractions that are not linear or repeating in the denominator when decomposed are not tested on the AP BC calculus exam. If you go to a really good the reason I know this is if you go to topic 6.12 in the AP Calculus AB and BC course exam and description, on page 126, it cites how some rational functions can be decomposed into sums of ratios of linear non-repeating factors. But nothing about nonlinear or repeating factors are ever mentioned in terms of partial fraction decomposition. What I mean by this is, like, I have this example down here. You might recognize something like this from AP Pre-Calculus. I remember doing it when at least honors Pre-Calculus used to exist. But you won't have to ever worry about doing an integration of a problem like this where you have like bx plus c over x squared plus 2x. Pretty much whenever you do this, whenever you're doing an integration of partial fraction decompositions, the only partial fractions you're ever dealing with are going to be ones that basically have a constant over a x to the power of 1 term. Yeah, and so that's pretty much it. I hope this video made sense to you. If any questions, ask Miss Elliott. And yeah, good luck on your AP exam and any other exams you may have.